Okay, today we're looking at the quadratic function, and the graph of the quadratic function will be parabolas, which we'll look at in a minute. This is a standard equation for a quadratic function. The only requirement here is that a cannot be 0. So for example, if a equaled 1 and b and c did equal 0, we would have f of x equals x squared, or y equals x squared, which is the simplest quadratic function, which we actually looked at in section 3.1 when we did transformations. Okay, now we're going to look at the function as it's described above. Okay, let's look at parabolas. If we were to graph this function, we'll figure that out later. The graph of a quadratic equation kind of looks like a U or an upside down U. So for example, let me sketch something in here. Something like that, or maybe something along these lines here. And they go on forever. So the first thing to notice is, and it's not apparent, but we did look at it in transformations, when a is positive, the parabola goes up. And when a is a negative value, the parabola opens down. Now, the point where the parabola changes direction, like right here, goes from down to up, or here, that's called the vertex. The vertex is a point that we'll use later on for solving application problems in a couple sections down, and it'll also be important for drawing the graph of a parabola, which we'll do in the next section. Okay. So when you look at the shape of the parabola and the vertex, you notice one thing. It looks like the shape on one side kind of mirrors the shape on the other side, and that's true. And it mirrors about a line, a vertical line that goes right through the vertex. I'll draw one here. And that vertical line is called the axis or line of symmetry. The book uses the word axis. And that is just the equation of a line where x equals a. So for example, here it would be x equals 3. That's the equation of this line right here, which happens to be the axis of symmetry. Also notice, and my drawing's not very good, but the points also mirror each other. So if I'm at 3 here and I go 2, 1, then I should go 4, 5. They're the same distance away from the line of symmetry as you move up the curve or down the curve. Okay, let's look at intercepts next. If you notice this curve, it has a y-intercept at 2. This curve right here doesn't look like it has a y-intercept, but remember, this curve is continually spreading out as it moves down, so at some point way down here, it's going to intercept the y-axis. So one thing to note is all parabolas have a y-intercept. And it's easy to find. Remember, If you look at the y-intercept, what is the value of x? 0. So that means the y-intercept occurs at x equals 0. So if we were to plug x equals 0 in up here, you can see that the y-intercept equals c. So it's very easy to find from this equation. C is where the parabola crosses the y-axis. If you wanted to write it in a point form, that would be when x is 0, y is c. That's your y-intercept. Okay, what about x-intercepts? Well, when the parabola crosses the x-intercept, those are the x-axis, those are x-intercepts right there. So I got a couple of them here on each parabola. And again, notice what happens here. When we're on the x-axis, y is 0. So to find the x-intercepts, all we need to do is let f of x equals 0. And solve that. We solved these, I believe, way back in section 1.5. These are just solving quadratic polynomials. And you can go back and look at the techniques there, but I think you remember them. You just factor this, set each factor equal to 0, and those are your two intercept points. Or you can use a quadratic equation, plug in a, b, and c, and get your two x points. Which, by the way, x-intercepts, when you solve this for 0, they're referred to as either roots or zeros. So the roots or the zeros of this function are where it crosses the x-axis. Now, are there always two? No. Let me draw a couple of more parabolas. You can see some things that might happen here. What about something up here? Or maybe a parabola here, or even one here. That's going to just touch. These two have one x-intercept only, and that happens to be where it touches the x-axis. It's not going to hit the x-axis anywhere else. So we can have two x-intercepts. We can have one intercept. Now, for two x-intercepts, you're going to do what we talked about above. You're going to have to use a quadratic function or factor. But what about one x-intercept? That's easy. If the vertices or the vertex is on the x-axis, then that's when you have one x-intercept. So this occurs when the vertex falls on the x-axis. So for example here, this vertex right here would be at x equals 4, y equals 0. That's the x-intercept, or you could say it touches the x-axis at 4, either way. Okay, is there any other possibility? Yes, this one. This one, even though eventually it'll cross the y-axis, it'll never come back down and cross the x-axis. So here's a case where we have 0 x-intercepts, none. Well, how do you find that? You can draw the graph, or you could look at the fact that the vertices is above the x-axis and it opens up in this case, that's fine. But what if you were just looking at roots? When you have zero intercepts, the roots or the zeros are complex numbers or imaginaries. So if you plug A, B, and C into the quadratic formula, and you get imaginary roots or complex roots, then you know that this parabola does not have x-intercepts. Okay. Couple things to look at here. First, actually maybe all we're going to look at here is the relationship to the vertices and the graph itself. In a couple of sections from here, we're going to look at solving application problems, i.e. word problems, where we're trying to find a minimum or a maximum situation. Well, it all hinges on the vertices if we're looking at a quadratic equation. For example, if I have a quadratic equation and A is positive, then the vertices, if I looked at the vertex, that should represent the minimum for the function. And you can see that on the graph. Here, A is positive, it opens up. There's the vertices. That's the smallest the function will ever get. It just gets bigger from there. Likewise here and here. We're starting at the vertices and we're just getting bigger or larger in number. And then the opposite, if A is negative, then the vertex is going to represent a maximum. For f of x. And again, you can see it if you look at this curve here. This parabola opens down since A is negative. If you look at the vertex here, you'll never get any higher than that. That's a maximum, so any other value would be lower. Likewise here, it's just going to get lower. Okay, so in our next section, we're going to learn some techniques on how to graph these things. We actually did some stuff in 3.1. 3.1, we started with the basic, and then we applied transformations. But we can go right from this equation here and get the points we need to sketch a parabola without having to do all the stuff we did in 3.1. So we'll do that next, and then the section following that, we're going to use the we're going to read word problems and figure out how to create a quadratic function from the word problem, and then we're going to look for a minimum or a maximum. Basically, we're going to look at the vertices, particularly the y coordinate of the vertices, to solve these problems. Okay.